I'm still paying you. I got the hard ass beats like the crack of the tech. I'm still paying you. Think y'all forgot what rap sounded like? I'm still paying you. Back to match up beats, the bang of the average. I'm still paying you. I'ma make y'all pay for the.
All right, let's get started. Round of applause for DJ Cash. Welcome back, everyone. You did a bunch of travels over the break.
Yes, sir. Yes, sir.
Went to LA
Went
and
to
San Francisco.
Yes.
See what, like, did you do any shows out there? Or are you just hanging out?
Oh yeah, DJing a little bit.
Yeah.
Here and there.
Okay. Did you live stream it?
My friend wanted to, but we didn't.
Okay, that's fair. All right, so hopefully everyone had a good break. I did because I only care about databases. I visited a bunch of database companies. We went to Snowflake, we went to Supabase, we went to PlanetScale, we went to Microsoft. Like, we talked about databases. It was awesome. And when we talk about query optimization next week, I can share what I think is from Microsoft with the one of the most brilliant ideas I've heard the entire year of how they're going to prove two SQL queries are the same, and they're going to use the query optimizer for that. So next week we'll see how it's not, kind of need to understand what the query optimizer is first. But when they told me what they were doing, I was like, oh, that's pure genius, because it's taking a SQL query, rewriting it with an LLM, and then need to prove that it's the same and use the query optimizer for it. Sorry, I'm getting way ahead of myself because I think the idea is awesome, but we can talk about it briefly next week. Today, we got to talk about how we're going to actually execute queries. All right, so for everyone, Project 2 is coming up this Sunday due. Again, the recitation video is available on Box, on Piazza. I think AWS is down this morning, so everything's broken. So you couldn't probably get to Gradescope and to AWS, but it should be up now. I haven't checked, but it was broken this morning. And then we're having the special office hours this Saturday on the 25th at 3 o'clock, same location on the 5th floor. And then for the midterm grades, they've been posted on Gradescope and Canvas. And then if you want to view your graded exam with the solution, come to my office hours on Wednesdays, and you can sit down with it and look at it. Okay? Who here has not started Project 2? Really? Okay, wow. All right. It's not going to be good. That's not good. I warned you. All right. Project 2 is much harder than Project 1, so please start immediately after class, okay? All right, so other database things going on. So today after class, we have the guys from Columnar who are building, there's a thing called Apache Arrow. Think of like it's a file format similar to like Parquet or Orc or Vortex, but it's in memory. So this is a way to transfer data quickly between different systems. So Arrow is used everywhere, and then they have this Arrow database compatibility or database connectivity API. It's a layer that sits in front of your application and the database server, so you can send data back and forth between your application and the database server much more quickly. This is used in pretty much every single modern system. So that'll be our talk today at 4:30. Tomorrow, I'll post this on Piazza when it comes back online. We have the guys from Astronomer coming give a tech talk on the 8th floor at noon. So there'll be pizza here for this one. Astronomer is the main company building Airflow. This is like an orchestration layer for sending data from one system to the other. And I know we posted for internships and jobs from those guys on Piazza. So they're coming on campus tomorrow to give a talk about that. And then I'll follow up with people if you want to meet with them to have like a small group session about discuss internships and jobs. We'll arrange that in the afternoon before they fly out. And then next week, same time will be on Monday, the seminar series will be the guy from Single Store to expand upon what he talked about in this class, okay? Again, all this is optional, and I'll post about the Astronomer stuff on Piazza later today. All right, so last class before the break, we were discussing different join algorithms, join operator implementations, nested loop joins, sort merge joins, and hash joins. Right, so now at this point, we've covered the basic building blocks you need to be able to run queries. We know how to sort data, right, whether it's in memory or out of memory. We know how to do aggregations. We know how to do joins. And so starting today and for the next 2 weeks, now we put all these pieces together in a conceptual system we'll describe as we go along. But now we can actually start executing queries. So we can take the buffer pool that we built. We can take the page layouts we've designed. We can take now these operator implementations. We're going to mash them all together into a single system and actually start executing queries. So that's what really today's about, and the next class will be about. Next week, we'll jump on the query optimizer, and that'll be how to take a SQL query and convert it into a physical plan that we're going to talk about how to execute today, okay? So again, as a reminder, again, the query plan in a relational database system is going to be a DAG of operators, right? Ideally, it's a DAG. Most systems implement a tree, but a tree is a subset of a DAG. The idea still holds. And again, the idea is that we're going to be moving data up logically, and I'll explain what I mean logically versus physically in a second. We're moving data logically between these different operators till we get the root of the query plan, and that's the final output that we send back to whoever requested the query. Whether it's an internal query, we keep the data for ourselves, or an application, or somebody sitting at a terminal. Right? The root is always going to be the final output that we send out to to outside the system. But now we need to slice up this query plan a little bit further and talk about pipelines. And pipelines are just, again, these logical boundaries we're going to use to denote that we have a sequence of operators where tuples can flow continuously between the operators, right, going from the bottom to the top. And we can keep going up across these operators, and we don't have to stop or wait for more results, right? And a pipeline breaker will be the operator that's going to be at the root or the top of one of these pipelines that can't finish or can't give any output to whatever's above it until it gets all the input of its children. So in my case here, assume we're doing a hash join, although in this plan, again, it's just the join symbol. We're not saying what the actual algorithm is. We're saying we're doing a hash join. We're going to scan R and build a hash table on that. Well, that's the pipeline we really only can have. We have the scanning R, populate the hash table, and then we can't execute anything else until this pipeline finishes, because we can't do the join and start probing the hash table until we know that the hash table isn't populated, because we could get false negatives. So you'll see this also in sorting, right? I can't have my sort operator produce any output until I sort my data, right? Because I can't tell you what the order is going to be until I sorted everything. So these pipeline breakers are going to be a way we're going to denote the boundaries of where we can do as much work as we can on single tuples or batches of tuples, and we don't have to get more data until we reach one of these pipeline breakers at the top. The reason why it's called pipeline, because it's like the old days in the 70s, was the idea was like, it's so expensive to go get a tuple from disk, so I can, one of these bottom scan operators on my tables, I'll get one tuple and I'll write it up as far as I can up into my pipeline, and don't go back and get the next tuple until I reach my pipeline breaker. Right? I'm gonna do as much work as I can with data that I bring into memory as I can, and not have to like write things out the disk unnecessarily. So that's again the high-level model what we're dealing with today. And the reason why I was trying to be careful saying what logically versus physically moving data, because going back here, right, it's clear from this diagram, it looks like data is being sort of pushed up, but most systems don't do that. Actually, data is actually pulled up physically. So that'll be the processing models. We'll cover that first. Then we'll talk about access methods, like what are the actual leaves of the query plan? How are we actually getting data from our tables? Because that's something we haven't really talked about in detail. Then we'll talk about how we handle modification queries. So insert, update, deletes, merge, and upserts. And then we'll finish off talking about how we're actually going to evaluate the expressions we have in our where clauses or join clauses or whatever it is to actually produce the matches or do filtering, whatever a query wants. Okay? You good? Okay. All right, so the query processing model is going to determine how the system is going to execute a query plan and move data between those different operators in the plan, moving data sort of from one operator to the next. And just like we saw when we talked about storage models, between like row store versus column store, there's going to be performance trade-offs and also engineering trade-offs between these different processing model approaches. Right? One's going to be better for OLTP, one's going to be better for OLAP. And so each processing model is going to be comprised of these two types of communications or execution paths in our query plan. One is going to be the control flow, and that's how the database system is going to say or to instruct an operator to execute, right? And how we're encapsulating what the operator code actually is, whether it's a class or a function or whatever, it doesn't matter. But there's something that's saying in the database system, say, hey, go run this operator, do your work. And then the data flow is going to determine how the operator is going to send data from one operator to the next in our query plan. Right? Logically, I'm showing the directed arrows going up from the bottom to the top. It doesn't necessarily have to be that way. Right? And then the thing that we also need to worry about is what is the output of these operators? And we're sort of loosely saying tuples, but we talked about the difference between early materialization and late materialization before, right? We said sometimes where in late materialization, maybe you just pass along the bare minimum columns you need, and then a record ID so that if some part of the query plan needs more data, it knows how to go get it. In early materialization, you basically instantiate the entire tuple. You may throw things away with projections, but that's fine. But basically, you never go back into the tables and get more data. Everything you need is being moved up to the query plan. All right, so the three basic approaches are the iterator model, materialization model, and the vectorized or the batch model. The original, for the last one, the original papers referred to as the vectorized model. Of course, now if you Google vector databases or vectorized databases, you're going to get all the RAG vector index stuff, or even the SIMD stuff. But you can just think of this in batches. And the way to think of this on as we see as we go along, the iterator model is going to be sending sort of the smallest amount of data from one operator to the next. The materialization model is going to be sending all the data from one operator to the next. And then the batch model is going to be setting a subset. And in terms of how common these are in the real world, most database systems you know about and can think about are going to be using the first approach, right? Postgres, MySQL, SQLite. The OLAP systems like the DuckDBs, the Redshifts, the Firebolts, the ClickHouses, those guys are going to be using the bottom one. The middle one is actually very rare. There's maybe 5 or 6 systems that actually use it, and 2 of them I wrote. So there's not that many. But we'll go along each of these one by one, and we'll see the advantages and disadvantages of all 3 models as we go along. All right, so the most basic model, or the simplest model, the most common model, is the iterator model. This is sometimes called the volcano model, because remember that guy that invented or wrote the book on like B+ trees? He had a very famous project in the late 80s, early 90s called Volcano that defined not only how you do this iterator model, but also how you parallelize it. We'll see that next class. And also how you build a query optimizer, all in sort of one project. It's very influential. That was also called Volcano. We'll see that next week as well. But it's not to say that this thing didn't exist before this guy wrote the paper in the late 80s. Again, all the systems in the 70s and 80s were doing this, which is now, you could call it the volcano model, and someone who's familiar with the research area would know what you're talking about. But in the textbook, I think, defines this as the iterator model. So in our database system, every query plan operator is going to implement a next function. And the contract the next function has is that when one operator calls next on another operator's next function, or invokes the next function, that operator's next function either returns back the next tuple up the query plan, or like a null or end of file to indicate there are no more tuples, and at which point the calling operator will never call next again, because there's no more data that could arrive or could be used below you at that point in the query plan, right? There's obviously also an open and close functions to like think of like a constructor deconstructor in C++, basically saying, hey, I'm going to tell the operator, hey, I'm going to go read some data, get ready. And maybe you instantiate an iterator on an index or open a file handle, whatever. And then the close basically saying like close up whatever, free up whatever ephemeral memory you've allocated for this, right? And again, it's also called the pipeline model because it's again the simplest form of this. So just moving things up in a pipeline. So I normally don't like to show code in class, but for this, it's pretty simple. And so I don't think this should be too taxing for you guys. But here's our query plan, right? And you can think of each of these operators are going to have their own operator implementation that is going to have this sort of pseudo Python code here, right? And so think of each of these functions or these blocks of code as implementing the next function for the different operators, right? And to sort of keep this simple, we're going to number them from 1, starting at the top and going to the bottom. So the way you start executing a query in the iterator model is you start the database system's sort of runtime engine, the thing that's actually scheduling queries to execute, will invoke next on the root, right? And the next function is the next implementation for that top operator, which is the projection. It knows that it has some number of children that it can call next on to go get data that it needs. So the top next function calls next on the next guy, and this is our hash join here. And so we have the left side and the right side. So on the left side, we got to build the hash table. So it's going to call next on its left child. And that gets down now to the scan operator on table R. And now you see inside this, we just have this for loop iterating every single tuple in R. I'm obviously hiding like, how do we get it from the buffer pool? How do we find the pages? All that, we know how to do that from earlier lectures. But inside that for loop, we just have this emit function. And that's basically like returning the next tuple that up to whoever called next on this operator. If you've ever written like a Python generator, there's like a yield function. So I'm not showing how we're freezing state inside of our for loop. Think of the same sort of way you would do this in Python, right? And obviously in C++, it's a little more, it's a more complicated, the more machinery you got to do, right? So this in operator 2, it's calling next over the left child, and down below we're just feeding up tuples from table R, and then inside the for loop for the left child in operator 2, I'm building my hash table. And at some point, the operator 3 says, I don't have any more tuples for you. And at which point, operator 2 knows I never need to call 3 again. So now let me go down my right side of my branch, my tree, and call next on my right child. That has its own for that calls next on its child. Now this is just scanning tuples from S and emitting them up to do the probe inside the hash table, right? And then if I have a match when I'm doing my join, then I emit that up into my projection operator, which then can emit that up to whoever called or invoked the query. So for the pipeline for this is that we have one on the right side here, pipeline 1, because I call next on my left child in operator 2, and I keep ripping through tuples in R until I don't get any more. And at which point I can then switch over and start executing pipeline 2. And then if you kind of think about it, for one tuple that I pull out of S at 5, I could pass it up to 4, check to see whether the predicate values are true. If yes, I pass it up to 2. Then it checks to see whether if I probe the hash table, I have a match. If it does, then I pass it up to 1. It does the projection, and then it produces its final output. So I've sort of pipelined the entire all the processing for the tuple on this side of the tree. So the great thing about this model is that it's a pretty simple interface. It's just open, next, close. So I'm not even defining how we're actually doing this scan here at these leaf nodes. In some systems, I may actually want to scan the entire table, materialize it in an in-memory buffer, and just keep track of a cursor. Every time you call next, what's the next tuple I want to hand out? Or you could do it sort of eagerly. Anytime you call next, go get the next tuple on the page, and then if it's that page if I've already scanned that page, go get the next page. So I could do everything all at once and just materialize the output and wait to pass it up one by one, or I could do it one at a time. It doesn't matter, and the rest of the implementation of the other operators doesn't have to care. Wait, say it again?
Pipeline number 1 stalls the execution of pipeline number 2, right? It's anything to do that in parallel.
Yeah, so his statement is, and he's correct, like, let's not talk about parallel execution, right? Just the notion is that I can't go down I can't go down the right side of the tree until I finish scanning the left side. Now, there is a technique called symmetric hash joins where you actually kind of do both, but we don't need, nobody does that. What's that again? Yeah, if you're doing a merge sort join, like you'd have to scan and sort everything. Well, yeah, so his point is, if I was doing a sort merge join, I could scan and sort both of these guys in parallel, then once they're both done, then combine them. That's next class. Let's worry about that. Keep it simple, keep it single-threaded. But your intuition is correct. All right, so hopefully this shouldn't be like mind-bending for everyone. It's pretty basic. This is what BustHub is using, so you'll see this in Project 3, right? It's easy to implement, it's easy to debug, because I just hook up GDB or pick your favorite debugger and just walk through all the next functions and see how things move around, right? And like I said, it's easy to run as a single-threaded model. Next class, we'll see how to parallelize it, right? And the advantage is that I can pipeline a bunch of data all the way through my operators without having to go get the next tuple. So I want to go as far as I can up until I'm done. right? And some systems go take this to the next level, and I'm just talking about keeping things in our memory. And in other systems with this pipeline model, they'll try to keep things in CPU caches, or like the Germans try to keep things in CPU registers because that's the fastest memory you can have all the way up, and that's really fast. But for that, we don't need to worry about that. All right, so the iterated model is being great for OLTP because it's going to get one tuple at a time, because most of your queries only need a small number of tuples. So the overhead of this is actually pretty small, right? Another nice thing about this model too is that for when you have limit functions, limit operators, like going back here, like if I only need the first 10 tuples that come out of this, it's really easy for me to implement that because I just put the limit above one, above two, and I just stop calling next when I have enough tuples for my output, right? I'm sort of blending the control and the data flow all sort of in one channel, but it does make certain things easier than it would be for other things. Of course, there's a bunch of downsides, like the function calls and next can be expensive, especially if you're trying to rip through a billion tuples. Like a function call doesn't seem like that much, but like in modern CPUs, that's expensive. And you have to do this for a billion tuples, that's going to start to add up. All right, so another approach is called the materialization model. And it's basically the same thing, but it's the iterated model, but instead of passing up one tuple, I'm going to pass up all the tuples from an operator. And at which point, I'm basically calling next once, and I never go back and ask for more data because I know I've gotten everything I could ever want, right? Of course, the problem's going to be with this is like, if I only need a subset of the data, like if I have a limit clause, then I don't want to have to pass up a billion tuples between different operators just to get to the limit at the top. It says, oh, I only need 10 out of these a billion, right? And so we'll see this in a second. You basically do operator fusion where you can kind of start merging down logic that would normally be up above in the query plan. You start putting it as low as possible or embedding inside of operators so that I'm not doing a bunch of redundant work or passing around data that I end up throwing away or don't need. And then just like before with the iterated model, right? When the data I'm passing could either be the entire tuple, could be late materialization with a record ID and some columns or a subset of the columns, right? There's tricks you want to do to like try to reduce how much data you're sending up. And that matters a lot in the materialization model because, again, I'm sending all the data up. So this technique was developed in the 1990s. It was a system called MonadDB that came out of CWI. CWI is basically where DuckDB comes from, or the co-founder of Snowflake did his PhD there, and he invented, basically they looked at this, saw this was terrible in MonadDB, and then the guy built a better system that then he went off co-founded Snowflake that fixed this. DuckDB fixes this too, but we'll see this in a second. All right, so now in our operator implementations, we have, which again, we still have these for loops. We're calling, get next, or calling output on our children. But now in these operator implementations, I don't call like a yield or a emit to send things in piecemeal. I just have this output function that I'm returning, or out buffer, and I'm returning back all the tuples to whoever asked me for it. So at the very top of the projection, we call down into this join. The join then calls down to its leaf node. Again, I'm just going to scan through R, just add all the tuples in my output buffer, return that up to my to the join operator. It then builds the hash table. Then it calls on the right side down its children, goes down the tree, and then sends back up the tuples in their entirety, computes the join, and produces the final output. So again, if you think about, always thinking in extremes, if table S has a billion tuples, and you look at this side of the pipeline, what am I doing? I'm scanning S, putting every single tuple in a buffer, then passing that to the filter operator, who then is going to look to see which one of those tuples I want to throw away. So again, if you have a billion tuples, but I only get like 10 of them, I don't have to pass a billion tuples up just to find out I need 10. So with operator fusion, the basic idea is that you combine together the operators in the query plan so that as I'm scanning the table, I can then apply my filter and throw things away. This is basically how you can do the same thing in an iterator model or the vectorized model, but it's a big deal in the materialization model just because you're passing along so much data. Seems crazy, but why would you ever want to do this? Let me take a guess. What's that? He said they're stupid? No. The guy who invented this is probably, he's dead, but he's one of the best database researchers of all time. So no, he's not stupid. If you always need all the data, or if it's, the guy who invented this, it was an OLAP system in MongoDB. They were assumed that you would need all the data within a column, but not all the columns. So they would do projections as operator fusion and throw away a bunch of these columns and just the columns you don't need, and only pass up the columns you do need, right? And then now you don't pay the overhead of calling get next, get next, get next for just to get all the columns from one operator to the next.
If you use the operators together, then it doesn't really matter which model you use because it's all one big fuse loop at the end.
The statement is, if you do operator fusion and you fuse everything together, which you can't, you can fuse things in pipelines, but not always. Then it kind of just one giant program. Again, if you have a pipeline, I can't fuse together. Some things I can fuse together, some things I can't. And the Germans are very good at fusing like almost all together. You can fuse everything within a pipeline, but as soon as I have to go cross pipelines, I can't do that. So for OLAP, no one does this except for, again, a very few systems. This actually works in OLTP systems because most of the time you're not getting a lot of data. So the overhead of having to call get next, get next, get next, if you can fuse everything together, because you're probably going to only have one pipeline, then it collapses down and becomes way more efficient. Again, this is for in-memory systems. It matters a lot, because I'm not worried about fetching things from disk. I'm trying to reduce my number of function calls I have to make. For OLTP, this makes a huge difference. But in most systems, most OLAP systems don't do this. Like HiRise was an experimental system out of Germany that started implementing with this approach, and then in the rewrite they got rid of it and switched over to the vectorized model. We'll see it in the next slide. Then RavenDB is a document database system. Think of it's like MongoDB but out of Israel, and again they're doing OLTP, so it makes sense in that environment, right? It's a simple model, easy to code, easy to debug. And it's not bad until you start getting with really large data set sizes or intermediate results, then it falls apart. All right, so the best approach for OLAP is going to be the vectorized model or vectorization model, and that's going to be somewhere in between the iterator model and the materialization model. So instead of passing along a single tuple or all the tuples, I pass along a subset or a batch of them. And different systems have different batch sizes. I think DuckDB is like 1024, right? It's not going to be in the millions. It's going to be some multiple of a power 2, like 1024 or 2048, something like that. So you're still going to have a next function, but again, so now instead of passing along a single tuple, you're going to pass along a batch or a vector, right? And then within we're not going to go into too much detail for this for this course, but there's a bunch of logic, or there's different ways to handle the case where I know my batch sizes are 2048, but if I start filtering things out in a batch as I go up, do I wait to get more data down below to fill that batch up back to 2048 or 1024? Or do I just pass along whatever I have up the query plan and let it be sparse as you go up? There's pros and cons to each of the approaches, but for this class, we don't need to worry about it. It's more about like, how do we keep track of this? Or how do we actually just sort of implement the basic idea of this? All right, so again, going back to our approach here, or sorry, our example here, right now in our operator functions or our next implementations, now we see that instead of passing along, instead of calling emit immediately when we have a tuple as our output, we are maintaining an output buffer, but it's not the full, it's not going to be some large chunk of memory that we would have in the materialization model. But now that we check to see anytime that our output buffer is full, then we emit it up, right? So now again down here, I'm going to scan through table R, add a tuple to my output buffer, and then only if the size of the output buffer is greater than n, where it ends my batch size or target batch size, then I pass up the tuple batch. And I do the same thing down below over here. Right? Pretty straightforward. So this idea seems obvious. It's only existed since like, I don't know, 2006, 2007. right? Even in the OLAP systems that were around in the 90s or 1980s, they were still doing the iterator model. In the case of MongoDB, they were doing the materialization model. And like I said, the guy that was a co-founder of Snowflake was at CWI, saw MongoDB do the materialization model, thought of a better way to doing it in this batch approach. And then he did a startup that got bought by Ingress, which was one of the first relational databases, but then they killed off that project. And then he went and founded Snowflake with 2 guys from Oracle. And then Snowflake is the behemoth that it is today. But pretty much every new database system that does OLAP, targeting OLAP workloads in the last 10 years is going to be doing this approach. And again, the size of the batch will vary. 1024 is probably, just, anecdotally, I would say is probably the most common one. There's a bunch of other optimizations that you can do now because you're dealing with batches that we're not going to talk about. But if you know what SIMD is, or single instruction, multiple data items, like now that I'm operating on a column of data that's all the same, that is going to be aligned together in memory, I can shove that in my SIMD registers and do a bunch of processing in parallel. It's really, really fast. Or I can shove things down to a GPU if I wanted to and do processing on parallel on those batches as well. Right? So the data system is going to have really efficient implementations for now these operator kernels, because they're just ripping through these arrays or these vectors very, very efficiently, and you're basically doing the same amount of work for a bunch of tuples all together, and that's the best thing for a modern CPU, because I don't have a bunch of branches or conditionals. Like I'm taking a batch of data and hanging a tight for loop, just do whatever processing I want on it, and then pass it up, right? And again, there's way more systems that I'm showing here, but every system that does OLAP nowadays is going to use this approach. And even systems that started off the iterator model abandon it and switch over to the vectorized model. All right, so we have this iterator model, the materialization model, and the vectorization model. In all the examples I showed now, we assume that there's this next function that I kick off the query processing for a given query plan by starting at the root, calling next, and then that sort of percolates its way down the tree, and data starts moving moving towards the top, right? So I'm essentially pulling data from the top of the query plan by calling next. I'm sort of pulling it up between the operators up into the query plan to reach the top, right? Now this is how most database systems are going to implement this. So this is sort of independent of whether I'm doing vectorization or iterator model. In all 3 of those different processing models, I can have this next function extraction and do that pulling of the data up. We would call this loosely we call this the planned processing direction. And so the first approach is this, what I just said, what I've been showing you so far, is again, calling next, pulling data up. But there's a whole other approach where you actually start with the bottom and push data up. And this is why I was trying to be careful saying, like, oh, when I show the query plan at the beginning of the lecture, I'm saying, oh, this is logically how data is going to flow. But the implementation, the physical implementation, could actually be different. So in the push-based model, it is kind of like, again, thinking at how the diagram is drawn in the logical plan. Like I'm going to start at the leaf nodes, and they're going to do whatever processing I have on them, and then move data up. So I don't even start at the root and call next down below. There is really no next function. There's some higher level scheduler that says, here's all the operators I need to execute, or here are the pipelines I need to execute. And then it knows how to invoke them individually, which may not be sort of the same bottom to the top order. It can decide on its own how to reorder the pipelines to execute based on what it thinks is the most efficient plan or efficient strategy. So let me show what I mean by this. So we have these 2 pipelines here. And again, each of them will have their own operator implementations, right? The first pipeline here, we're just going to be scanning table R, and then we'll build some hash table. And then for our second pipeline, we're going to take all the tuples in S and probe whatever hash table got built down below us, and then emit them if there's a match after doing the projection. So I'm doing operator fusion here within my pipeline because it's just take one tuple and run it through those individual operators until I produce my output, right? But there's no direct connection, there's no emit function anymore, or next invocation between these different pipelines. I just know I have these 2 pieces of code. They're going to get data from somewhere. They're going to write data somewhere. And then now I have a high-level scheduler that they can say, well, here's all the tasks I need to execute within my for this query, it can then decide in the order in which it wants to execute them. But it knows the dependencies of the data that between these different pipelines. So no, it can't run pipeline 2 until pipeline 1 finishes populating the hash table. So it would invoke pipeline 1 first, and then now there'll be part of this task that we're executing here. There'll be some notion of there's a location of where I can write my data to, right? As I produce my results. So as I build my hash table, I could just be allocating pages in my buffer pool and writing my hash table out to there. And then when I get full, I can get more pages. And then when my operator 1 is finished, the scheduler says, oh, well, 1 is finished, but I know task 2 was waiting for task 1 to produce results. So I can now schedule to execute task 2. And oh, by the way, task 2, here's the location of the data that the first task wrote to. So if you need to go get its output, here's where to go find it. Right? And then it can do the same thing. It's going to produce some output that it has when it does the join and the projection. And right to that output buffer, when the task finishes, the scheduler knows here's the final location of the data that this second operator produced, or second task produced, and it knows that's the result that one sends back to whoever asked for the query to execute. So I'm separating the notion of like the control flow and the data flow, meaning like the scheduler is saying execute this task, execute that task, and it's not trying to piggyback off like that next function to say, all right, this guy calls this guy, calls this guy. Because that's basically the same scheduling mechanism, but it's implicitly happening because of the way the next thing sort of propagates down. But now I have these discrete tasks, and I can have a more global view of what's going on in my query, and I can make better decisions how I want to schedule things. Again, so the push model, because I would schedule the leaf nodes first, and they were sort of pushing data up rather than me starting at the top and working my way down and pulling data to the top. So there's pros and cons to all of these. Again, it's way easier to implement the top to the bottom, the pool-based approach, and most systems are going to do this. Right? It's easy. We talked before. It's easy to control the output for my limit clauses because I know how to basically stop calling next when I know I have enough data. Right? In the case of the bottom to the top of the push-based model, you can have a better implementation of these operators that can be more careful about where they're putting data. I'm showing to write to generic output buffers, but you can start doing things like within my fused pipelines, put things in registers, and then make sure that the next task gets scheduled can then maybe read those registers or something, right? For some operators, it can be difficult to implement, like a sort merge join, because I have to sort two things separately and then run a task that then does the join. Whereas I could have if I'm doing the pull-based model, I could have a single pipeline, assume that the first result is sorted, then sort the second one, and then just feed things up through that way. But that's a low level detail you don't need to worry about. So the top one is way more common. The second one I would say is rarish. The most famous system that probably started implementing this approach was Hyper from the Germans. And then this found its way into Umbra. It's the second version of Hyper. But AductDB started off actually using the top one. And then they realized that was a mistake, or they realized that it was a better idea to do the second one, do the bottom one here. So they switched to that. But they originally didn't start this way. ClickHouse does this. CWB is a commercial fork of Umbra. Firebolt does this. Snowflake does this. Like the major OLAP systems all do this approach in combination with the vectorization model. But again, those two design choices are independent. So I could do vectorization model with the pool-based approach. Data Fusion does this. A bunch of other systems do this. But the second one has a bunch of advantages, but you maybe don't only realize until you actually implement the first one. Yes.
So in processing model, can multiple approaches coexist, or the database system has to make a choice that this will be trigger approach for all queries or vectorization?
This question is could a database system support different processing models? So not the plan direction, but the processing model. So iteration, materialization, and vectorization. Yes, in theory, yes. Nobody does that because it's now you got to implement everything, or a bunch of different things, right? And it makes it harder now to potentially compose things together. I mean, you basically can get the iterator model if you implement vectorization, or actually really all of these, by just having your vector size be 1. it's the same thing. It could be less efficient because you're going to put things in an output buffer, right, versus just passing along a single tuple. But it's basically the same. But nobody would do that because now you're maintaining, different variations of the same thing, and that becomes an engineering nightmare. It's just not worth it.
So, in your slide from approach 1 to approach 3, there were some names that were common on both. Does that mean that they used to implement integrator and then evolved into vectorization, or they have evolved?
Yeah. So his question is, so say go back to let's do iterated model and then the vectorization model. So in this slide here, I'm showing Oracle, I'm showing SQL Server, right? Just focus on those two, and then or DB2 as well. But then when I jump over now to the vectorization model, Oracle's here, DB2's there, and SQL Server's there. So in the case of Oracle, we didn't get to talk about this, but they actually run dual engines. So they'll have a column store engine and a row store engine all within the same binary, but they're separate code bases. So technically they support both. Same with like SQL Server. They have like a column store engine. So basically Oracle, SQL Server, DB2, all these systems are from like the 1980s or 1970s. And so they're all row-based pool iterator model implementations. And then when column stores and OLAP stuff became more common, they realized, oh, our implementation is not efficient, right? Vectorization model is better. Let's ignore the push-based thing. Vectorization model is better, and passing and being a column store is better. So they had separate engines that can use these different approaches. But within one engine itself, it won't switch. That would just be a nightmare to maintain. Okay, cool. All right. All right, so now we're going to talk about access methods. So now we know conceptually how we're going to move data up from the different operators or move between different operators. Okay, I don't mean to use direction, but like I think you understand between the different approaches now. All right, so the access method is going to be how you get data from the leaf nodes, right? Because in relational algebra, there wasn't a definition. We didn't say, oh, here's a sequential scan operator, or here's an index operator. It was just like I do a filter or a projection or a select on a relation, but I didn't define how I'm actually going to get the data. So now in our implementation, we have to worry about that, right? So there's three basic approaches. You either do a sequential scan, that's the fallback approach. Like no matter what, I can always sequential scan the data. But if I have an index, then there's a bunch of different ways I could go at this, and I can either choose one index and do an index scan, or in some systems, I have multiple indexes. I can do index scans on all of them, or some portion of them, and then be clever about how I combine the results to put it together. Right, so we're really focusing right now, like how do we actually do this bottom part here? And like I said, the sequential scan is the easiest thing to implement. Assume you're doing a heap-based system. It's just going to the page directory, getting whatever the first page is, reading, scanning it, finding tuples, and then emitting them or putting them in a buffer, or however it's actually being implemented. It doesn't matter. I'm going page by page and reading data out and shoving it up to the next operator. And basically, the database system or the operator implementation will maintain its own cursor that just keeps track of where it left off in the last page or the last tuple that I looked at, so that if it calls next again or it has to require more results, it knows where to pick it up where it left off before, right? And alternatively, you could just materialize everything, scan all the pages, put it in a buffer, and then just scan through that or iterate through that and shove tuples up. But that obviously has problems, because if it's a large table, I got to put it somewhere in memory, and I may it may not be the most efficient way to do this, right? So again, sequential scan is the fallback choice. It seems like, again, if I have no indexes, no other way to get data, I can always just read the pages one by one. So this seems like this would be terrible and very inefficient, except that we've already talked about a bunch of different ways to make this go fast, right? Right? We've already covered a lot of these things in previous lectures, like data encoding compression. What was that? That was taking data and converting it into a different binary form that exploits repeated values, repeated data, so that when I go fetch a page from disk, to do my sequential scan, I'm reading more tuples than I would otherwise if it was uncompressed. All right, we talked about how to do prefetching or scan chaining, I think we skipped buffer pool bypass. Basically direct copy things into memory space for a worker. But prefetching was a big deal. It was like, if I know I'm going to scan the data sequentially, go fetch a bunch of pages ahead of time, bring them in memory so that when I need them, I don't stall waiting for disk. They're right there available for me. Task parallelization, multi-threading, we'll see that next class. Clustering, sorting, again, if I'm doing, I can do binary search over sorted data, or I can do sort merge joins over sorted data much more efficiently than just if it was unsorted. Materialized views, or sorry, materialization we've already talked about, like passing along bare minimum data I need. Materialized views and result caching, we won't cover this semester. Result caching basically is like, if I execute the same query over and over again, and if the data hasn't changed, why execute the query again? Just give you back the last result. That is rare. Most systems don't do that. Materialized views is where the application tells it, hey, I'm going to execute the same query over and over again. And so pre-compute the results and give it back to me, the cache results when I run the same query, or a query that looks or that could be answered by the materialized view. Of course, the challenge is, how do you maintain the freshness of that materialized result? The high-end systems can incrementally update the materialized view. Like every single time, if I'm computing the sum of a column, every single time I insert a new tuple, I don't have to scan all the tuples and recompute the sum. I can just increment or decrement based on what new value gets inserted or updated, right? Postgres can't do that. Postgres can't even do it automatically. You have to tell it when you want to refresh the materialized view. So we're not going to cover that this semester. And admittedly, to do the sophisticated materialized views, that's the part of data systems I know the least about, because it's really tricky. And very few systems do this. Data skipping is basically, we'll cover in a second. Data parallelization, vectorization, we'll see in the next class. Code specialization and compilation, I'll talk briefly about this at the end of the class here. I'll show what Postgres does. It's basically saying, well, if I know I'm going to be executing this, I know I'm going to be executing this query, rather than me interpret that and walk through that query plan tree, let me just generate a program that does exactly what the query wants to do, compile that, and that's going to be way faster than interpreting. So Postgres will do this for the where clause. They won't do it for the whole things. The Germans do it for the whole things. And again, we'll cover the end of this class. All right, so I'm going to go through data skipping, because again, this allows us to avoid reading data we don't actually need if we know we don't need it ahead of time. And then we'll cover these other ones in a second. So there's two ways to do data skipping. The first is not that common. It's called approximate queries. Basically says, well, if I don't really need an exact answer, don't read all the data to compute the exact answer. If I want to get the number of visitors on my website for a given month, do I really need to know may not really need to know the exact count of the number of visitors, right? If I round it to the nearest 1,000, if my website's getting millions of views, that's good enough. So in the high-end systems, there are, in addition to all the aggregate functions we talked about before, like count, min, max, sum, average, there's approximate count, an approximate min, approximate max. They're basically doing sampling. And the better systems can give you sort of statistical guarantees about how accurate the sample is. And if I really need the full answer, I'll just do a complete scan. Zone maps is way more common. Most systems do this. Most file formats support this. Basically, it's like a pre-computed aggregation on a column, so that depending on my query, if I know that I don't need, if I can look at the zone map and see that the data that the zone map represents can't be satisfied for my predicate, I don't bother reading it. It's like a filter, right? It can't tell me whether can't tell me where the data I may want is. It can tell me where a block of data would even have the data that I'm looking for. And this is super common, and it's in pretty much every system uses this. So say we have a simple column like this, right? A single column with integer value. So my zone map could say, like, for these set of values, here's the min, here's the max, here's the average, here's all the aggregations I may want to compute on this, right? Sometimes you also use like the number of null values, right? Basic statistics. Min, max, and number of null values are the number of distinct values, the most common ones, but you can pretty much throw anything in there, right? And pretty much all the file formats of Parquet, Orc, the Vortex one from last week, that talk, I think the guy's giving a talk this Wednesday as well, they all support basically the same kind of thing in their file formats. So now if my query shows up, select star from table where value is greater than 600. So say, again, I'm only showing 5 tuples here. Right? Say again, if think in large terms, I have 1 billion tuples. So I can look in this zone map and say, well, I only want to look for values that are greater than 600. So I look in the zone map, and the zone map says, well, my max value in this block of data is 400. So I know there can never be a match for me in this block of data, so I don't even go bother reading it. I read the zone map, and that's smaller. Yes? The question is, how do you choose what approach you want to do in terms of going back here? So the first one is lossy, right? So you're going to get wrong results. Is that okay? Well, the data system doesn't know what you care about, right? It's your company, your organization, your startup, whatever. So maybe, for certain queries, that's okay. The data system can't infer that because that's an externality that it can't know about. So you have to say, I want approximate this, approximate that, right? You always do this one. You always do the bottom one because it's always a huge win. Right? If it's your bank account, do you want to have an approximate count on your or sum on your balance? No, right? Data system can't know that. All right, so there's a paper. So the Oracle term is called zone maps. Sometimes you see these called SMAs or small materialized aggregates. It's a paper from '98. Basically defines it in this way, right? Again, it seems kind of obvious, but it didn't really come out until the 1990s. And this guy here, Guido, he's a German. So this is the PhD advisor of like the #1 German that does the Umbra and Hyper stuff that we talked about many times. So this is his PhD advisor. So the Germans are ridiculous. All right, so that's pretty much everything you do with sequential scan. We'll talk about compilation or code specialization at the end of class. So let's talk about index scans. Again, we know what index are being used for, right? We saw this before, how to figure out how to use a B+ tree or a skip list or whatever the data structure we want to find the tuples that match whatever we want to satisfy in our predicates in our query. Now the challenge is going to be how to determine which index to use. Like if I have a bunch of indexes I can use on my that are available to me in my tables, and my where clause actually references a bunch of columns that are being managed or referenced by a bunch of indexes. Which one is going to be the best one for me to use? That's a hard problem, and that's what we'll cover next week. So for now, we're going to ignore how do we pick what the best index to use is. So assume some Oracle has, not Oracle the system, but the company, some Oracle has figured out this is the best one you use. So now we can talk about how we actually want to go ahead and use it. So the way to think about this challenge is like, we're trying to reduce the amount of work we have to do, and it's going to depend heavily on what the data looks like and what our predicate looks like. So say we have a query here. We want to get all the students that are less than 30 that are in the CS department and come from the US. But I have an index on age and department. So one scenario, there's 99 people under the age of 30, but there's only 2 people in the CS department. But the flip side could be there's 99 people in the CS department, but only 2 of them are under the age of 30. Is that me? Shit, sorry. Sorry. My lawyer. All right. Right. So in this case here, it's kind of obvious, right? So if I have more students that are in the CS department, but only 2 people that are under the age of 30, then I want to use that age index because I can quickly go get those 2 students that are age 30, and then let's go check to see whether they are, in the CS department or not. And the flip side, if I have more people that are under the age of 30, I want to use the department one because that's more selective. So this is basically what the data system is going to try to figure out for us. And then once we figure out this is the index I want to use, based on the API that's available to us that the index exposes, then we just invoke that API in our operator to get the data that we want, right? In a B+ tree or a skip list or a try, I can do range scans, but I can't do that in a hash index. So the data system also has to figure out, all right, my predicate has an inequality or a less than for so my SQL query has a less than for age, but it equals for department. So if I have a hash index on age, I can't use that to satisfy this query, so it'll pick another index. And then we just invoke the API to get the data we want out of it. The cool thing is that we may not always have to make a single choice of like what's the one index I want to use out of all my indexes. Some systems let you use all the indexes or as many indexes as you want, and then you just do the probes or do the lookups on those indexes you get back the record IDs that match whatever your predicate is, and then you just do either a union or intersection between the results of different indexes to find the tuples that you want. So some systems will call these multi-index scans. Postgres calls this a bitmap scan because it's going to build a bitmap and then do intersections on the bitmaps. MySQL calls these an index merge. They're all basically doing the same thing, right? And if the predicates in your where clause across the different indexes are they're conjunctions or and clauses, then I just take the intersection of the two sets. Or if I'm doing an or disjunction, then I take the union of two sets. Then I have all the record IDs that match what are the predicates across all my indexes, and then I go fetch them from the table to go get actually the results I need. So we're going back here to our example again. So we have doing a lookup of all the students that are aged less than 30 in the computer science department in the US. Assuming I have an index on age and department. So, and they're both equally as good. So I'll retrieve all the, do a lookup on the age index to get all the tuples that are less than 30, or sorry, the tuples where the age is less than 30. Then I'll do another probe in the CS department and get all those tuples that are in that department. And then I take their intersection, and then I go get the tuples that match the intersection or that are still in my intersection result. Then go see whether their country is US. So visually, this looks like this. Probe the first index, get all the records that are less than 30. Probe this index, get all the records where the department is computer science. Take the middle part, the region here, the intersection, fetch those records, then just do an additional lookup to see whether the country is US, right? Because there's no index for me to do that. Pretty straightforward. All right, so now we got to talk about how, so we now do selects. We do either index scan, a sequential scan, or a multi-index scan. The basic idea is the same, right? And then depending on our processing model, we're either batching them a bunch of tuples or sending one tuple at a time. It doesn't matter. For tuples that modify the database, insert, update, deletes, we're basically going to piggyback off of the basic access methods that we have and all the other operators we have to modify these databases so that we don't have to re-implement, like in the case of a delete or an update, we don't have to re-implement scan operators to go find tuples that match our predicates. We just reuse the scans we used for selects. And then now the output of those scan operators are then used to then do whatever the update or delete. For insert, the basic idea is that you decide whether you want to materialize the result as a separate operator or within the insert operator. And I'll show that next slide. For other operations like upserts, merges, truncates are easy. You just drop the table and then add it back, right? Upserts are basically scans followed by updates if there's a match or insert. Right? They all basically work the same way. Right, so update deletes, we're just going to use all the scan operators, access methods we talked about before, and as they pass up the record IDs, that's what then used inside of these modifying operators to then change the data as we need, right? We got to be careful though, keep track of any tuples that we may see before, because if, we'll see in the next slide, if we start scanning data on an index and we start modifying data and we physically put it somewhere back in the table or an index that the iterator hasn't got to yet, and then it comes across it again, we don't want to have to modify it or delete it multiple times. For inserts, again, you either materialize the tuple inside of the insert operator itself, or you materialize it on the outside. And if you do the last one, then you can do like select into, you can do like create tables off of select statements. Like it's easy to compose these things together because the insert operator doesn't care how tuples are coming into it from down below it in the query plan. It just says, take this and put it into this table. I can do that. So, but again, we have that decoupling of the concerns or the logic for populating tuple buffers. Then we can have whatever went below us in the query plan generate tuples. As long as it's in the right form that we expect, following our API, the insert operator can insert anything from anywhere. Right? You can do temp tables and everything using this as well. All right, so let's see this problem about updating things multiple times. All right, say we have a table of people, and we want to keep track of their salary. And I want to run a query. We're going to update everyone's salary. I'm going to add $100 bonus or increase their salary $100 in the end of the year if they make less than $1,100. So assuming we're going with the iterator model, going from the pull-based approach from top to the bottom. I start at the top. I'm going to start scanning all the tuples from my child. It goes down below, and now in this second operator down here, then I'm going to do my index scan, and it's going to instantiate an iterator that's going to just scan across all the leaf nodes and find tuples and then emit them up to the next operator. So the first thing it finds is me, and I make $999. So that gets passed up now to the operator above it. We then go inside the for loop, do the update, add $100 to it, and then write it back out to the index, right? So then, now, we go back down to call next on the child operator again. We scan across even further, and then now we come across me again, right, with my updated salary, and then now I'm going to update it twice. And that's obviously bad, right? But what's happening here? We're changing the physical location of data in whatever data structure is being used at the leaf operators, right? I'm moving, my record Andy used to be over here because this is indexed on my salary. But when my salary got updated, it got moved to another physical location on the leaf nodes. And then the iterator goes along and then it finds it again. So this is a very famous problem from IBM. It's called the Halloween problem. And next week's Halloween, so I always like to bring this up. Right? So it's an anomaly in a database system implementation that occurs when the physical location of a tuple changes that causes a access method or a scan operator, whether it's an index scan or a sequential scan, to come across or see the same logical tuple multiple times because its physical location has changed. Like logically, there's only one Andy, in the, not the world, whatever. There's one logical Andy, but physically in my database, during the execution of this query, it physically moved different locations. So it doesn't know, it didn't, at least in the simplistic implementation, a naive implementation wouldn't know that it's seeing the same logical thing. It sees distinct physical tuples. So this was discovered by the IBM researchers in the 1970s, 1976, when they were building System R, which is one of the first relational systems ever built, right? It has nothing to do with Halloween. There's like the original use case wasn't Halloween. They discovered this problem on a Friday, late Friday afternoon when they were building System R, and they were like, "Oh, this is hard. What do we do?" And they were like, "Oh, I don't know. It's Halloween. Let's figure it out on Monday. Let's go out and drink." And they just left the problem and they solved it the next week. So it just happened that they discovered this on Halloween and went drinking and didn't solve it that day. That's why it's called the Halloween problem. And there's a Wikipedia article explicitly calls this out. All right. So again, it's just the way to handle this is sort of obvious. You want to keep track of like, have I seen this logical tuple, multiple times, or did I modify this tuple I'm looking at to know that I don't need to modify it again, right? It's sort of obvious how to do this. You have to handle this in Project 3. I'm only bringing this up to say like there's a bunch of logic that I'm not really showing here inside of my scan operators, where I'm keeping track of actually what I actually am modifying. And whether you keep track of like, here's the things I modified in a separate buffer, or you can record in the header of the tuple, like this thing was modified by me, therefore don't look at it again. There's different ways you can implement this, and they will see this in 2 weeks when we start talking about concurrential, how to handle it. All right, so for the end of this class, I want to talk about how we actually handle expressions. So it's sort of obvious we have these where clauses that we want to evaluate to determine whether tuples match, whether there's a join or a filter or whatever it is. So now we have to talk about how do you actually execute these things. And the way you represent this is just another tree. So within our tree query plan, where each operator can have its own trees that represent the expressions that they're responsible for at that sort of level or that point in the tree, right? So for our join clause, where RID equals SID, and the where clause, s.value is greater than 100, well, this is just a conjunction between the join clause on the two tuples, the two tables, and then the evaluation on the value based on whether it's greater than some constant here, right? So basically, while a query is executing, as you're scanning the data, you have to evaluate this tree to determine whether the predicate matches or whatever the operator wants to do, whether it satisfies this expression defined in this tree to determine whether you should be moving tuples up to the next operator, to the next stage in the query plan. So let's look at sort of simple example like this. So we haven't talked about prepared statements, but think of it like a macro I can have declare in SQL. So I have prepare XXX as, then I have my select clause, and now you can see inside this my select clause I have where.s.val equals $1, so parameter 1 plus 9, right? And so I call prepare on my application, and I say, hey, I'm going to execute this query a lot, give it a name, XXX, and then now when I want to execute it again, instead of calling that entire select query, I can say execute and treat it like a function, say execute query XXX, and pass in the parameters 991, and that'll get substituted in $1 up there. Some systems would the basic idea is like, instead of me having to run the query optimizer for every single time I'm going to build this query, I can prepare it ahead of time, cache it, and then reuse the query plan over and over again. Of course, there's trade-offs to this, whether it's a good idea or not. Like, depending on, for some values I may pass in because I don't know it. I don't know all the values when I call prepare. Some might have one query plan versus another. Right? There's no free lunch. Sometimes it's a good idea, sometimes it's a bad idea, and different systems do different things. Postgres will automatically generate these prepared statements for you when you run the same query 5 times. Right? Other systems don't do that. All right, so as I'm scanning my data, my operator, I'm going to have this execution context that's going to keep track of like what's the tuple I'm looking at, what are the parameters that are passed in when I invoke this query, and what's the schema of the table I'm looking at. So now when I evaluate my tree, different operators in my expression tree are going to need different information from the different contexts. So all that I want to have ahead of time so that I'm not doing these lookups every single time, because I'm trying to rip through this expression tree as fast as possible, because I'm doing this on a per tuple basis. If I have 1 billion tuples, I got to walk this tree 1 billion times, and I want this to go as fast as possible. So you basically are doing depth first search, right? I'm going to start at the top, or depth first traversal. My equal sign here, I know I want to go down to the left side, so I want to get the value for the attribute s.val. So I again look up in my execution context and say, oh, well, I know that I need s.val, my current tuple, and is that offset based on the schema? So I can just then extract out the value 1,000 here. Then I traverse down to the next side of the tree, and said, all right, well, this leaf node here wants parameter $1. I look at my execution context, see that I'm being passed in 991 as that parameter. And then I go down to this side here. I just materialize this constant 9 to come back up to the addition operator, add these two values together, get 1,000, and then come back to the root and say, does 1,000 equal 1,000? If yes, emit true, otherwise emit false. And then whoever invoked this tree to do this evaluation here takes the output and decides, okay, as I'm scanning this data, does the tuple match this predicate? And the tree tells me whether it does or not. Do you think this is a good idea or a bad idea? It works. It's what? It's good. Why?
Because it works.
All right. You know what? I can't. Yeah, I'll take that. Yeah. Can we do better?
Compile it.
Say compile it. Yes. And we'll see that in a second. Yes. So it's terrible for the CPU because I just made a big point about how like the materialization model was trying to, and the vectorization processing model was trying to remove all the overhead of calling next. But now within, even I'm passing along a batch of tuples to remove those next calls, I got to evaluate that tree, and that's kind of a bunch of indirection for these for these operator pointers, right? And that's gonna be really slow. And so what I really want to be able to do is just evaluate the expression directly and not have to traverse the tree, because it's pretty simple what we're doing here, right? So my example, where s.val equals 1, and I have my tree form of this, well, that's really just a function called check that returns true if value equals 1. So if I can avoid that overhead of traversing the tree and just invoke this function, then it'd be way faster. And if I'm running on a batch of tuples, like in a vectorization model, I can hope my compiler will automatically auto-vectorize it using SIMD. Or if not, I could use intrinsics to write it myself. But now I could pass along, instead of a single tuple, I could pass a batch of tuples. They're all just checking whether something, the value equals 1, and that's going to go super fast on SIMD instructions. And then their suggestion was to compile it into machine code. And some systems will compile actually the whole query plan systems like Postgres will compile a portion of it. So let's do a quick demo of that. I'll turn off the light so you guys can see better. So, all right, so this is going to run Postgres. Log in. So I have I made a simple table called fake data with, as you expect, with fake data, right? And it's just a bunch, oh, sorry. Thank you. There we go. Okay. Sorry about that. All right. So it's a table with a bunch of fake data, right? There's nothing fancy about it, right? And I think there is 50 million records. Yeah. Okay. So first thing I'm going to do is I'm going to run this special function in Postgres called pg prewarm. That basically just does a sequential scan. It brings everything from the table into the buffer pool, right? So I'm going to turn off the just-in-time compilation for the where clauses in Postgres. I'm also going to turn off parallel scans because we'll cover that next class. And then so I'm going to run some query that produces, I'm going to run some query that does some kind of computation where there's a where clause, I'm doing a match, but I don't have an index on this, so I basically have to scan everything to see whether I have a match. So without doing any just-in-time compilation, it's going to take a few seconds. And so this, I'm running, notice how I put explain and then analyze, and then I have my parentheses. I want it to give me the explain output. Analyze tells it to actually run it and produce the time it takes to actually run it. And then buffers just tells me tell me whether how many pages you read from the buffer pool versus how many pages you read from disk. And so it's just for my own sanity, I'm making sure that everything in this table is in memory. So it says shared hit equals whatever the 200,000 pages. So I know that everything's being read from memory. So this query executed in roughly 4 seconds. If I run it again, it'll take about the same. The planning time is telling you how long it takes in the query optimizer. So it takes about 200 milliseconds. And then the query is always going to take 4 seconds, right? So now if I turn on just-in-time compilation, Postgres added this 5 or 6 years ago. And so what this is going to do, it's going to take the where clause, generate the instructions in the LLVM, in LLVIR, for actually executing exactly that where clause. So instead of having this like traversing the tree, I basically flatten the tree and generate the instructions to do exactly the work that the tree wants to do. Right? And now if I run it, it should be, yeah, there we go. So now it took 2.7 seconds, right? Whereas before it was taking 4 seconds. So I saved about a second. But you notice here, there's this extra output here where it says JIT functions equals 4, and then it has the time it takes to do generation, inlining, and the optimization. So it looks like it added about 381 seconds to do the JIT compilation. So it's paying an overhead up front before it executes the query to do this compilation, but in the end, it made the query run a lot faster, so it was a good trade-off. And Postgres has its own cost model to determine, it knows roughly how long it takes to JIT things. It has an estimate of how long it's going to take to execute the query, so it can decide whether it actually to JIT things or not, whether it's worth the trade-off to pay that extra cost. Right? But Postgres is a row-based system that's doing a doing an iterative model with a pool-based approach. So with JIT compilation on, and I'm not doing parallel execution here, but it wouldn't make that big of a difference. But Postgres' best effort here can run this query on this data in 2.7 seconds. If we cut over to DuckDB, and it's the same data, but I'm going to execute the same query. Just explain and analyze. So with DuckDB is not going to do any query compilation, not JIT compilation. It's going to be do a push-based column store with a vectorization model, right? It completes the query in half a second, or sorry, less than a second, right? So all the extra machinery that Postgres is doing to JIT things, which is not a trivial thing to write, it's in debug, right? That's a major engineering effort to add that. DuckDB still crushes it. right? And I'm pretty sure make sure this is single threaded, right? Single threaded, right? Less than a second. So again, there's engineering trade-offs because Postgres is a row store, and it's using the iterator model. It's going to be great for OLTP, not so great for OLAP. But if you design a system specific for OLAP, you can do way better, and that's what DuckDB does. Firebolt, ClickHouse would all have similar results. All right, so quickly to finish up, there are some additional optimizations we can do in our expression trees other than just compiling it. So you can do simple things like constant folding. If you ever take a compiler class, it's all the same tricks, but now it's in the context of databases, so it matters more. Right? So if I see that I'm going to be calling the upper function on the string Wu-Tang over and over again, if I have a billion tuples, I'm going to call this function a billion times for this constant. So I just recognize that, okay, well, I only need to actually execute this once, compute it once, and then inject that as a constant, and I never have to call it again. Right? Common subtraction elimination is another simple thing you can do, right? If I see that in my query, I have a conjunction that's basically computing the same thing, or sorry, disjunction computing the same thing, right? This string position on X within a column, right? So this whole portion of the subtree over here is the same as this subtree over here. So rather than me executing it over and over again for every single tuple duplicatively, I can recognize that they're actually the same, just rewrite the expression tree to be able to reuse the results of the calculation as it occurs over there. Right? And the data system can do this for you automatically. You don't have to rewrite your SQL. Right? It can try to figure out the best way to actually execute these expressions in the same way it's going to try to figure out the best way to execute your query. And we'll see that next week. Okay? Wait, say it again? So his statement is, and he's correct, if I'm saying the LLVM is going to do this, GCC is going to do this, Clang is going to do this, would I still want to do this in my database system, even if the compiler is going to do it? So in case of Postgres, the JIT thing was added 6 years ago, and not every query is going to get the JIT capabilities, so you still don't want to do this. There are some systems where they try to use a compiler for everything. There's an experimental system from the Germans where they will use compiler to like a classical compiler to optimize the query plan itself, and also optimize all the expressions as well. They do it all at once. I don't say the big Germans, but the hyper Germans, the Umber Germans, they will do this as well, but then the LLVM will do its own sort of passive optimizations as well. The reason why they do this separately is because the way they do compilation is they do in two-stage. So they'll take your query plan, generate assembly. So they generate x86 assembly, run that in an assembler. That's super fast to generate. Run that, and then in the background, they invoke LLVM to start compiling your query on that assembly. And then if the compilation finishes before the query finishes, then they slide in the compiled shared object to replace that. So in the assembler version, if you want that to run fast, you still have to do this. But doing this is it's not hard to figure this out. All right, so sorry, I was making sure I was still recording. All right, so I hope I conveyed today that the same query, the same SQL query can be executed a bunch of different ways, whether it's index scans or sequential scans, using top down versus bottom up, right? And different data systems do different things, and depending on what your workload is and the environment is that you're trying to target, you're going to choose one versus another. In general, for OLAP, you want to definitely do the vectorization model. And then depending on your engineering tolerance, you could do a push-based model versus a pull-based model, right? I can't say definitively there's not one better than another because it is a bunch of trade-offs for all of them. For LTP, you want to use index scans as much as possible. So therefore, if you know you're not going to read a lot of data and everything's going to be in memory, then materialization model probably is going to be the better way to go, right? The expression trees are a nice abstraction to represent expressions. And as he said, they're good because they work, but there's ways to make those go faster, okay? All right, so this is all single-threaded execution. Next class will say, how do we take the same things we talked about today and now add multiple workers, and how do we combine them results to produce the final result, okay? All right, hit it.
Money, flick, flips, acrobats over tracks. Cash money, flick, flips, acrobats over tracks.
never strain, flow with the grain. It's fortunate, motherfuckers man. Maintain, but never strain, flow with the